Welcome to Lab 9 Part 1, where we will program 3 numerical differentiation formulas, which are the forward, backwards, and centered finite difference formulas. To get started, we will import the 3 libraries. First, we need to import SymPy as SP, then NumPy as NP, and finally Matplotlib as PLT. In this lab, we will take the derivative of the Rung function, which is 1 over 1 plus 25 times x squared. First, we will translate this as a SymPy expression. First, declare x as a SymPy symbol using the symbols function, passing x. Then our Rung equation will be equal to 1 divided by 1 plus 25 times x squared. Next, we need to generate some data of our Rung function from -1 to 1. So here we will use x values equal to numpy.arange between -1 and 1 with a step size of 0.1, and our y values will be our equation evaluated at each of our x values. So here we will generate a matrix where the first column is x and the second column will be our equation at x. So Rung.substitute x with I for I in x values. But first we will generate the actual derivative using SymPy's diff function. We will set x actual equal to numpy.arange between -1 and 1 and with a step size of 0.01. Then the actual derivative will be equal to Rung.diff with respect to x. Substitute x with I for I in x actual. Let's go ahead and display our y values. And we will also plot the derivative of our function, which is x actual and y actual. Then plot.show. Here you can see our y values is a matrix where each row contains a point with the x values and the y values, where the column at index 0 is our x values and the column at index 1 is our y values. And here you can see the graph of the derivative, which we will use as a comparison when programming our finite difference equations. First, we will cover forward finite difference, which depends on the Taylor series expansion shown here. We can rearrange to find f prime at xi to get this equation. You can see here that the error term is directly proportional to the step size h. You can also see that the equation contains a f at xi plus 1 and the xi plus 1 term. This means that the derivative can only be found up to the second last data point, but not the last one. Because we can only find the derivative when there is a successive data point. We will declare our function as FFD with the inputs x, which is a list of our data points, and then we need n equal to the length of our data points. And then we need our xp list, which will be the derivative of x, and our xval list, which will be the x values. Then we will loop I through the range of 0 to our second last data point, which is n minus 1. First, we will append our x value to our xval list using xval.append, where the x value is xi, which is our ith row, and the x value is at column 0. We must append the value of the derivative to xp using xp.append, where the derivative will be this formula, where the numerator is f at xi plus 1 minus f at xi. Here f at xi plus 1 is x at I plus 1, index at the column 1, minus x at I at index 1, divided by the denominator, where the denominator is x at I plus 1 minus x at I. And this will be x at I plus 1, index at the 0th column, minus x at I, index at 0. Finally, we will return both the xval and the xp list. Now that we have our function, we will set the return values equal to x and y, and then call our function FFD and pass in our y values. We input the y values, which are the data points of the Rung function, and the output is the derivative of that Rung function. x and y using a list comprehension, where the first column will be x and the second column will be y for I in range of the length of x. Then we will plot a scatter plot of our x and y, which are the results of our forward finite difference formula. And we will compare this to the actual derivative, which we got using SymPy's diff function. Finally, we will plot a grid as well as plot.show. So here you can see the derivatives x and y returned from our FFD function. Here you can see our graph where the dots represent the data points from our forward finite difference formula and the line plot is our actual derivative. As you can see, the data points from the forward finite difference is slightly shifted backwards when compared to the actual derivative. Since the derivative at each point is dependent on the next data point, we are able to take the derivative up to the second last data point, but not the last one. Next, we'll take a look at backwards finite difference. The main difference between this and the forward finite difference is here instead of f at xi plus 1, we have instead f at xi minus 1. And instead of x at I plus 1, we have x at I minus 1. So this means we can only take the derivative when we have a previous data point. So we must go from the second data point all the way to the last data point. Notice here that the error term is also the same as the forward finite difference. I will now copy the code for the forward finite difference and make some changes. Here we will change FFD to BFD, and once again BFD. We will also change the range. Instead of starting at 0, we must start at 1, and we must end at n. And here the formula is also slightly different, and the only changes we must make is from I plus 1 to I minus 1, and once again here. And here from our data points, you can see we start at negative 0.9 and end at 1. Now from the graph, you can see the data points from our BFD are slightly shifted to the right of our actual derivative, since the data points depends on the previous data point. You will also see we are unable to find the derivative of the first data point, and we must start at the second data point. However, unlike the forward finite difference, we are able to find the derivative of the last data point. Centered finite difference, which is more accurate than both the forward and the backwards finite difference, since the error term is now directly proportional to the square of the step size h. Now looking at the formula, the centered finite difference is basically the average of the forward and the backwards finite difference. Once again, I will copy and paste the code for FFD and make some changes. First, we will name our function CFD. Now, since we depend on both xi plus 1 and xi minus 1, meaning we need a data point both before and after our current data point, we must change the range from 1 to n minus 1. And the numerator of our function is f at xi plus 1 minus f at xi minus 1. So here we will make the change of xi minus 1. Then the denominator is 2 times h, where h stays the same, but we must times it by 2 and then close it by round brackets. And here we see our data, which starts from negative 0.9 all the way to 0.9. Here from the graph, we see that the centered finite difference gives us the best approximation for the derivative, since it almost directly overlaps our line plot. Note that we are also unable to calculate the derivative of our first and last data points.